This is SpaceTime, Series 23, Episode 15. Coming up on SpaceTime, discovery of a vampire star in the midst of a feeding frenzy, solar orbiter launches on its mission to the Sun, and the growing problem of space junk surfaces again, with 2 satellites experiencing a near miss. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have found what they're calling a vampire star in the midst of a feeding frenzy. The vampire is actually a white dwarf, the white-hot stellar core of a dead sun-like star. And its victim is a brown dwarf, a failed star which didn't have enough mass to trigger the nuclear fusion of hydrogen to helium in its core, the process which makes stars shine. Astronomers made the discovery with the help of an automated program that sifts through archival data from NASA's decommissioned Kepler Space Telescope. The new algorithm acts like a sort of cosmic detective to find clues of very fast, mysterious explosions in the universe. Its aim is to find rare astronomical events that evolve rapidly over just a few hours or days. Things like gamma-ray bursts from the core of collapsed supernovae or colliding neutron stars forming black holes. The program detected something called a dwarf nova. A dwarf nova is a sudden outburst of energy around a white dwarf caused by the detonation of a ring of accumulated material around the star. That material came from a brown dwarf which is orbiting the white dwarf in a binary system every 82 minutes. The system, which is classified as a WZ-Zaghetti-type cataclysmic variable, has been catalogued as KSN BSC11A. The white dwarf's companion brown dwarf, which is just a tenth the mass of the white dwarf, is so close to the primary star that its outer envelope forms a tidal bulge which overlaps into the Roche limit of the white dwarf, allowing material to be drawn onto an accretion disk around the white dwarf. As the brown dwarf material builds up in this accretion disk, it increases in temperature until thermal instability causes it to ignite in a thermonuclear explosion or nova, peaking at temperatures of around 11,700 degrees Celsius and releasing gravitational potential energy. The Kepler data reveals the dwarf nova rapidly became 1,600 times brighter in just a day, before quickly dimming again and then slowly fading back to its original luminosity over the next 30 days. The authors say the next step for this project involves combing through more Kepler data and then extending the search to data from NASA's new exoplanetary space telescope TESS, the Transiting Exoplanet Survey Satellite. One of the study's authors, Dr. Brad Tucker from the Australian National University, says the data provides new details about some of the most rapid explosions in the universe. And he says along the way, astronomers may also discover some rare events that no other telescope could find.
So vampire stars are kind of a nice description of what's going on here. So led by my PhD student, Ryan, found a white dwarf, so something our sun will be in 5 billion years, and it was near a brown dwarf, so what we call a failed star. And because the white dwarf still had a lot of gravity and the brown dwarf got too close, the gravity of the white dwarf pulled off the gas in the atmosphere of the brown dwarf, caused it to pull around and actually started to explode. So kind of sucks the life, as it were, out of this brown dwarf.
The method used to find this was interesting too, wasn't it?
That's right. So Ryan used the Kepler Space Telescope, so famous for finding all those planets around other stars, but because Kepler was looking at such a large area of sky, we always had the idea that there was other things around it. So it's kind of like if you're staring straight ahead, well, you have your peripheral vision off to the side. We kind of looked around the sides to see these random things that popped up. So Ryan's PhD was essentially writing a way to trawl through all of these images to try and find something. So we didn't know this is what we were going to find, just to find something, these hidden explosions, because Kepler, because it takes an image every 30 minutes, we can see explosions that happen really quickly. And this is, in fact, exactly what he saw, this white dwarf destroying a brown dwarf in near real time.
And we use the term a dwarf nova to describe this.
That's right. So we know novas happen. So these are kind of their counterparts to supernova, involve a smaller star and a smaller explosion. But what we were able to see is that because we are taking all these quick images, we can see how quickly the main explosion happens, how quickly this dwarf nova happens. And by seeing how quickly it happens, we can measure exactly how far apart the two stars were. We can also measure how fast it happens and how hot it gets, measuring that it got over 10,000 degrees, the tens of thousands of degrees Celsius, to create this massive amount of energy that we saw.
Now, normally when we think of a nova, this is a buildup of hydrogen on the surface of a neutron star. And so a dwarf nova involves, I guess, the same process, buildup of mass on the surface of a white dwarf.
That's right. And it's similar to what we think causes some type 1a supernova, that you get a white dwarf near a main sequence star or red giant, the gravity pulls it off, builds up mass, and it reaches a certain limit and explodes. But because the brown dwarf is much smaller and there's less material, it doesn't do one big explosion, it does a series of smaller explosions. That's exactly what we happen here. One of these intermediate explosions in a star system not too dissimilar than what our own solar system might look like in the future.
Tell me about this star system. What do we know about it other than the fact that there's a white dwarf in the middle and it's got a brown dwarf, a failed star, orbiting it?
So we know it's in the constellation Scorpio, and it's about 3,000 light years away. The period, so how fast they're orbiting around each other, is about 82 days, so fairly quick, quicker than, in fact, Mercury orbits the sun, and really close in distance. So something the scale of the Earth to Moon. We're talking about something really close that got really too close in this. So it's a very unique small system. And, it's one of the interesting questions is we find lots of brown dwarfs. We find lots of hot Jupiter, so big planets near another star in all these solar systems. How are these solar systems going to end? We're trying to figure out the life cycle of stars, seeing how they're born, figuring out how their star systems are in their middle age. And what Ryan and I have been working on is how they end and how this all connects to it. So it's a nice, interesting piece of the stellar puzzle.
Being a white dwarf means it's probably been around for an awful long period of time, the host star, and having a brown dwarf orbiting it means the brown dwarf has probably lost a fair degree of mass over the period of time it's existed. There's a good chance this may have originally been a binary system with a sun-like star and a red dwarf.
Yeah, exactly. That's exactly right. As you said, we know this has to be quite old, much older than our own. And because of what we see, it probably was some other star. It probably was a binary star system that eventually fell to fate. And it very well could have had planets orbiting around it. If it has a brown dwarf and there's enough mass to create a brown dwarf and decrease, there's very likely that there was other planets orbiting this star system, and they would have orbited probably both stars, the white dwarf and the brown dwarf. And as they went through their stellar evolution, as the white dwarf was a red giant before that, it would have changed the solar system. It would have caused the bigger things to potentially migrate, move closer. So this solar system, the star system, has really probably undergone a lot of change in its history. And if we were to observe it 7 billion years ago, it would look completely different.
It would look a lot more like our own solar system in some ways.
It would. And I think kind of the nice thing about how these things come together is, we have to take snapshots of their lives, and we can't wait for one whole solar system to do this. So by looking at the thousands and the millions of them out there, we can put these pieces together and get a bit of fate of our own.
So where to now with this?
So this was kind of the first object that Ryan found in Kepler. He found lots of candidates, potential objects. We learned there's a lot of weird asteroids in our solar system by doing this experiment, but we think there's more of these things and other explosions out there. And now he's in the U.S. working on TESS. This is kind of the new version of Kepler, and TESS is looking at a much larger field of view, a much larger patch of sky. And by doing this, we hope to see more of these sort of dwarf nova, but also other types of short explosions, kind of probing a part of the universe we don't normally see, and that is explosions on the order of hours instead of weeks to months.
And of course, Tess is looking at as you said, a far wider patch of sky. Kepler focused on just one small area in the northern hemisphere.
That's right. And in fact, Kepler, because it was so far out, only downloaded about 1% of the pixels. So most of that in between sky, we weren't able to look at, whereas Tess is downloading everything every 30 minutes. So a lot more stuff to look through. So Ryan's excited about the more discoveries that will await him.
That's Dr. Brad Tucker from the Australian National University. And this is SpaceTime. I'm Stuart Gary. The European Space Agency's Solar Orbiter has blasted into space on its historic mission to image the Sun's polar regions and to study its magnetic fields in Heliosphere, the Sun's extended atmosphere created by the solar wind, which fills and encircles the entire solar system. The 1,800 kilogram spacecraft was launched aboard an Atlas V 411 rocket from Space Launch Complex 41 at the Cape Canaveral Air Force Base in Florida.
FDS count started.
Vent valves locked. Locking the vent valves will bring the booster tank and tanks up to flight pressure, getting everything ready for launch this evening. We just heard from the range officer that the range is green and ready to move forward.
The range is green. That is a big step moving forward. Everything's clear. Basically mean there is no nothing to impede launch, nothing out there in the water, nothing out there in the air. As we count down to the liftoff of an Atlas V rocket.
Status check. Go Atlas. Go Centaur. Go Solar Orbiter.
There you heard the final status check for booster Centaur and the spacecraft. Everything is go.
And so here we go. T-minus 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And liftoff of our solar orbiter and international collaboration to give us new images and a better understanding of our life-giving star. Listening now, you hear the voice of Patrick Moore, ULA's launch commentator.
Now 25 seconds in flight. Chamber pressure on the SRB looks good. Engine operating parameters on the RD-180 also look good.
Good report so far. Atlas V beginning to pitch over. 35
seconds in, vehicle is completing the pitch over maneuver.
45 seconds into flight, everything is looking good.
We heard that the RD-180 engine was operational.
RD-180 throttling down slightly as expected, and engine response looks good.
Pull those engines down for just a little bit as we anticipate max Q.
Now supersonic. Vehicle's now passing through max Q, maximum dynamic pressure.
At maximum dynamic pressure is the period of maximum mechanical stress on the rocket because it's reached its highest velocity and resistance created by the Earth's atmosphere. Made it through and they're throttling back up.
And standing by for SRB burnout. And we have burnout on the solid rocket booster. Atlas will hold on to the SRB for an additional 47 seconds prior to jettison.
They're going to let that thing go at 2 minutes and 19 seconds.
Now 1 minute 45 seconds into flight. RD-180 continues to perform well at full thrust. Pump speeds and injector pressures look good.
All right, stand by now for booster jettison.
And now coming up on 2 minutes into flight, the Atlas V vehicle now weighs just one half of its liftoff weight. RD-180 throttling down slightly as expected. Engine response continues to look good. And standing by for SRB jettison shortly.
There it goes.
Jettison of the solid rocket booster. Atlas V has gone to Q Alpha limited closed loop steering. Vehicle body rates look good.
Now the next major milestone is
now 2 minutes 35 seconds into flight.
At 3 minutes and 25 seconds.
And the second stage RCS system press valve is opened. System now pressurizing to flight levels.
Flying at over 5,000 miles per hour.
Now 3 minutes into flight, approximately 1 minute remaining until BECO.
He's talking about main engine cutoff. 1 minute.
RD-180 continues to look good. At pump speeds and injector pressures look good. 3 minutes 15 seconds in.
Right. About to cut that booster.
Vehicle body rates look stable. Now 3 minutes 30 seconds in. RD-180 now throttling to maintain a constant 5G acceleration limit. Engine response looks good. And we've begun boost phase chill down. Now throttling to a 4.6G acceleration limit. Boost phase chill down is ended. Standing by for BECO. And we have BECO booster engine cutoff. Standing by for stage
Atlas Centaur separation.
And we have good indication of Atlas Centaur separation. We have pre-start on the RL-10. Standing by for ignition.
Next major milestone is the payload fairing. When that comes off,
we have ignition and full thrust on the RL-10. Chamber pressure looks good. Body rates look good.
That payload
and we have good indication of payload fairing jettison.
Right now.
This first burn of today's mission will last approximately 8 minutes, and the RCS system is now performing initial firings to warm up the RCS motor catalyst bed. System response looks good, and the Centaur is now 100 miles in altitude, 450 miles downrange distance, traveling at 11,800 miles per hour. 5 minutes, 10 seconds into flight.
You're listening to the voice of Patrick Moore, ULA's launch commentator.
Centaur propellant utilization system has gone to closed loop control.
Flight is looking very good at this point.
And RCS system now performing periodic firing for thermal conditioning of the system. System response looks good. And initial review of booster performance shows the booster performed close to pre-flight predictions.
So the next major milestone will be the Centaur first main engine cutoff.
Solar Orbiter will track active regions on the stellar surface that might explode in powerful eruptions known as solar flares, or even bigger events called coronal mass ejections. See, different parts of the sun rotate at different rates, causing magnetic field lines extending out from deep below the sun's surface to twist, stretch, and eventually snap, producing these violent events which fling huge bursts of plasma and ionized particles, mostly protons, electrons, and alpha particles, or helium nuclei, deep into space, dramatically increasing the solar wind flux. When these solar storms smash into the Earth, they overwhelm the planet's protective magnetosphere, which shields the Earth from the solar wind and cosmic rays. The sudden wave of plasma and charged particles then flows along the Earth's magnetic field lines towards the north and south magnetic poles, in the process generating spectacular auroral displays, the northern and southern lights, the aurora borealis and aurora australis. But these same geomagnetic storms can also short-circuit, damage and even destroy spacecraft, overload terrestrial power grids on the surface, blacking out vast areas, interfere with communications and navigation systems, affect airline services at higher latitudes, and increase radiation exposure for astronauts and to a lesser degree for airline crew and passengers. And by causing the Earth's atmosphere to expand and contract, these space weather events can also increase atmospheric drag and orbital decay on spacecraft, shortening their operational lives. Science's understanding of space weather, its origin on the Sun, and its progression and threat to Earth comes with critical gaps that Solar Orbiter hopes to fill. Once deployed from its launcher, Solar Orbiter's systems and instruments were fired up and began an extensive in-flight test phase to ensure they've survived the rigors of blastoff. The probe has now entered a cruise phase which will last until November 2021. During this time, the spacecraft will perform 2 gravity-assist maneuvers around Venus and 1 around the Earth in order to alter its trajectory, guiding it towards the innermost regions of the solar system. The first close solar pass will take place around the end of March 2022, at around a third the distance between the Earth and the Sun. At this point, the spacecraft will be in an elliptical orbit that takes about 180 days to complete, making a close approach to the Sun every 6 months. The probe will take 3.5 years, using repeated gravitational assists from Venus and Earth, to reach its operational orbit, which is inclined at about 25 degrees above the ecliptic, the orbital plane where the Earth and other planets go around the Sun. By then, the spacecraft will have undertaken a close flyby of the Sun every 5 months, to within 42 million kilometres of the solar surface, far closer than the orbit of the scorched planet Mercury, and about a quarter the average distance between the Earth and the Sun. And each additional gravity assist orbit around Venus will constantly change the spacecraft's elliptical path, which will be continually tilted and squeezed, edging it ever higher and higher and closer to the Sun's poles. Now, if its initial 7-year mission is extended, additional gravity assists from Venus will further raise Solar Orbiter's inclination from about 25 degrees up to 34 degrees above the ecliptic, giving us never-before-seen views of the Sun's poles. Solar Orbiter scientists will also coordinate their observations with their counterparts working with NASA's Parker Solar Probe mission, which is flying closer to the Sun than any previous spacecraft, collecting data directly from the solar corona. Parker's scientific goals are to better understand the heating of the solar corona and the acceleration of the solar wind and energetic particles.
ESA's Solar Orbiter and NASA's Parker Solar Probe are space weather sidekicks on 2 separate but complementary missions to study our star, with the aim of being able to better predict when solar wind might pose risks to our communication satellites, electrical grid, and even astronauts. Professor Susan Lepre is Solar Orbiter's Heavy Ion Sensor Deputy Principal Investigator. Her team is in charge of an instrument that will analyze trace elements in the solar wind, determining its risk to technology in orbit and on the ground. Professor Justin Casper is Principal Investigator for Parker's SWEEP investigation, which measures the solar wind at extreme proximity to the Sun. Parker launched a year and a half ago on August 12, 2018 from Cape Canaveral aboard a Delta IV Heavy rocket. Orbiter is a bigger satellite with a launch mass of 3,968 pounds and will have an 18-meter solar panel wingspan. In comparison, Parker's launch mass was 1,510 pounds, and it's about 9 feet 10 inches long. Orbiter's bigger body is packed with an array of 10 primary scientific instruments, while Parker's payload carries 4 instrument suites. Parker had to be a lot lighter in order for its orbit to dip so close to the Sun, and it can't carry the same kind of hardware because of the extreme heat. For example, unlike Orbiter, Parker has no cameras that view the Sun directly. No current technology could look at the Sun from that close and survive. If Earth were scaled down to sit at one end of a football field and the Sun at the other, Parker would make it to the 4-yard line. Solar Orbiter will come within 27-yard line, which is still the second closest approach of all time. Where Parker collects up-close ground truth samples, Orbiter is further back and able to use its cameras in conjunction with other sensors to localize its samples to where they originated on the Sun. In other words, it can say this solar wind has these qualities and it came from a solar flare that happened on this region of the Sun. And at key moments, both Orbiter and Parker's orbits align so that they can do measurements on the same gusts of solar weather at different points downstream. This is important because those comparisons will show how the weather changes as it gets further away from the Sun. Another key differentiator is that Orbiter will follow a highly tilted orbit and provide our first ever direct images of the Sun's poles. allowing scientists to see how the structure and behavior of the solar wind varies at different latitudes.
While the Parker Solar Probe focuses on protons, electrons and alpha particles, the most abundant particles coming from the Sun, Solar Orbiter will also study heavier but far less abundant trace elements like carbon, oxygen and iron. Solar Orbiter's close-up high-resolution studies of the Sun and its inner heliosphere will provide scientists with a new understanding of how and where the solar wind plasma and magnetic field originate in the corona, how solar transients drive heliospheric variability, how solar eruptions produce the energetic particle radiation that fills the heliosphere, and how the solar dynamo works and drives connections between the Sun and its surrounding heliosphere. Knowing the composition will help determine where energy is being deposited and fed into the solar wind and eruptions on the Sun, as well as how particles are accelerated in the heliosphere. To do this, Solar Orbiter is carrying 10 scientific instruments, protected from the Sun's constant baking 520 degrees Celsius heat soak and intense bombardment of solar wind particles by a 30 centimetre thick titanium heat shield. These scientific instrument packages include a solar wind analyzer to measure the solar wind's properties and composition, an energetic particle detector to measure superthermal ions, electrons, neutral atoms and energetic particles, a magnetometer to study the Sun's powerful magnetic field, a radio and plasma wave analyzer to provide high time-resolution measurements of magnetic and electric fields, a polarimetric and helioseismic imager to grab high-resolution and full disk measurements of the photospheric magnetic field, a full sun and high-resolution imager to observe different layers of the solar atmosphere, a spectral imager to gather data on the photosphere and corona and to characterize plasma properties, a spectrometer telescope to image thermal and non-thermal solar X-ray emissions, a coronagraph to provide simultaneous ultraviolet and polarized visible light imaging of the corona, and a heliospheric imager to study the ebb and flow of the solar wind. This report from ESA TV.
Built by Airbus in the UK, engineers have had the challenging task of designing a mission to make detailed observations of the Sun, capture the closest ever pictures of our nearest star, and the first images of the poles.
The spacecraft has a number of key new technologies that have been developed just for the purpose of flying close to the Sun. We have a specific heat shield designed just for Solar Orbiter that will reach temperatures of over 500 degrees centigrade on the front side and will keep things as cool as just about 50 degrees centigrade on the backside to protect the sensitive electronics.
The Sun generates a bubble of plasma enveloping the entire solar system. Known as the heliosphere, anything within it, including Earth, is subject to a stream of charged particles called the solar wind. Violent space weather from flares and coronal mass ejections has the potential to damage satellites, disrupt communications and knock out power grids on the ground. Solar Orbiter will help answer fundamental questions about the Sun's activity.
One of the key questions the scientists have is how the heliosphere is actually generated and how it's accelerated. So what is really driving the solar winds? And the second key question of the mission is understanding what makes the Sun change or vary over this 11-year cycle that we all know. So understanding the magnetic properties of the Sun and how these change over this 11-year cycle is one of the key scientific objectives of Solar Orbiter.
To measure the magnetic environment around the Sun, Solar Orbiter is fitted with a suite of 10 extremely sensitive instruments. And so it can take pictures, the heat shield has peepholes through it, covered by protective doors.
We're going to places where no other solar telescopes have been before. We're going to be very close to the Sun to take very high-resolution images of the Sun, unprecedented spatial resolution, and we're also going to fly over the poles of the Sun, regions that are very much unknown because we don't see them very well from Earth, but they are the source of the fast solar wind and therefore are very important.
Solar Orbiter will take several years, using the gravity of Venus and Earth to reach its operational orbit. But once in position, the spacecraft will take measurements that complement NASA's Parker Solar Probe, which launched in 2018.
We will not get as close to the Sun, but we will have a vastly bigger payload complement, so more instruments with more cameras looking at the Sun. So we will do science that is complementary to Solar Probe, and the two will really have a great deal of synergy.
The engineers and scientists working on Solar Orbiter can now look forward to their hard work, revealing our Sun as never before.
And that report by ESA TV included ESA Solar Orbiter project scientist Daniel Mueller, ESA Solar Project Manager Cesar Garcia, and Solar Orbiter Principal Investigator Frederick Auger. Over the years, astronomers have sent numerous missions to study the Sun, all of which have focused primarily on the Sun's equatorial region. The one exception other than Solar Orbiter was the Ulysses spacecraft, which observed the Sun from a wide range of latitudes for nearly 2 decades until the mission finally came to an end in 2009. Despite Ulysses' insights, the focus on lower solar latitudes has left the Sun's poles relatively unexplored, which is where Solar Orbiter comes in. You're listening to SpaceTime. Still to come, the growing problem of space junk surfaces again. And later in the science report, we wrap up all the latest news on the COVID-19 coronavirus. All that and more coming up on SpaceTime. The growing problem of space junk has surfaced again with 2 disused satellites, each travelling at 28,000 kilometres per hour, missing each other by just metres. It all began with a series of tweets from Leo Labs, a company which tracks satellites and space debris using radar. Their data predicted 2 spacecraft could come within 15 metres of each other with a 1 in 20 chance of a catastrophic collision. The 2 derelict spacecraft involved were NASA's infrared astronomical satellite IRIS, a 1,000-kilogram space telescope launched in 1983, and the 83-kilogram classified GGSE 4 Cygnet satellite launched by the US government in 1967 to monitor radar emissions from the then Soviet Union during the height of the Cold War. Both satellites were dead, neither could be controlled or moved, and so all people on the ground could do was watch and see what unfolded. In the end, the probes did miss each other, but it was close. And it's not an isolated incident. The first major satellite collision we know of occurred on February 10, 2009, when the 560-kilogram Iridium-33 telecommunications satellite collided with the deactivated 950-kilogram Russian Cosmos 2251 military satellite. The collision occurred some 800 kilometres over northern Siberia at a relative speed of 11.7 kilometres per second, or 42,120 kilometres an hour, destroying both spacecraft and leaving a massive debris cloud. The most recent case happened just last month, when a disused Russian secret spy satellite, the Cosmos 2491, was suddenly hit by a piece of space junk, breaking into at least 10 major fragments. Of course, the International Space Station is routinely forced to maneuver out of the way of space junk, with the crew often needing to seek refuge in their Soyuz capsules in the event of a collision and the need to undertake an emergency escape. It was also common for America's space shuttle fleet to return to Earth after a mission in orbit with damage caused by both micrometeoroid impacts and often tiny bits of space junk. To date, the worst incident, polluting space with deadly shrapnel, wasn't an accident but deliberate. On January the 11th, 2007, China conducted an anti-satellite missile test using a DF-21 ballistic missile launched from the Xichang Satellite Launch Center to deliberately blow up a disused Chinese weather satellite in order to demonstrate to the rest of the world that they could do it. The missile slammed head-on into the 750-kilogram Fengyong FY-1C series weather satellite at an altitude of 865 kilometres, travelling at 8 kilometres per second, and smashing both spacecraft into a potentially deadly debris cloud containing hundreds of thousands of pieces of shrapnel. The event remains the largest recorded creation of space debris in history, with well over 2,000 pieces of trackable-sized debris catalogued in the immediate aftermath. One of the biggest fears scientists have about orbital collisions are cascade events. This is where bits of space junk slam into satellites, creating more debris, which then slams into other spacecraft, creating even more debris, and so on and so on. First proposed by NASA scientist David Kessler in 1978, the Kessler Syndrome involves a runaway chain reaction of collisions, exponentially increasing the amount of debris orbiting the Earth, to the point where the distribution of debris could render space activities and the use of satellites in specific orbital ranges impractical for many generations. The United States Strategic Space Command is currently tracking over 18,000 artificial objects in orbit above the Earth. Of these, only around 1,500 are operational satellites. The rest are disused spacecraft and spent rocket stages. But these are only the objects large enough to be easily tracked from the ground. Current estimates suggest there are around 950,000 bits of space junk a centimetre or more in size, and a staggering 170 million bits of space debris a centimetre or smaller currently orbiting the Earth. It's all a really big problem, and it's going to get a lot worse before it gets better. You're listening to SpaceTime. Still to come, the Science Report. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. There have now been some 1,500 deaths from the coronavirus, with around 70,000 people infected globally. That dwarfs the 774 deaths reported from the SARS virus epidemic in 2002 and 2003. New research reported in the Lancet Medical Journal suggests that in the early stages of the Wuhan outbreak, between December the 1st and January the 25th, each person infected with the virus would have infected an average of 2 to 3 other individuals, and the epidemic doubled in size every 6.4 days. Now, the initial data suggest the coronavirus has a fatality rate of around 2%. Now, by comparison, the SARS, or Severe Acute Respiratory Syndrome outbreak, which spread from Gansu province in China to 26 other countries, took 8 months to be contained and had a fatality rate of almost 10%. And the other similar coronavirus, the Middle East Respiratory Syndrome, or MERS, which began in Saudi Arabia and was transmitted from infected camels, has claimed 858 lives from 2,494 confirmed cases, resulting in an initially calculated fatality rate of a staggering 34.4%. But as additional data became available, that death rate was revised down to just 0.1%, well in line with other known human influenza viruses. Now, if we compare these 3 coronaviruses to something like, say, the bird flu influenza, we put things in perspective. Bird flu's actually been around since at least 1918, when it was called the Spanish flu pandemic. It killed an estimated 50 million people and infected 500 million worldwide. Bird flu, of course, has had a resurgence over the past decade or so, with strains like the H1N1 swine flu, the H5N1, and H7N4. In recent years, bird flu's infected more than 1,600 people, killing almost 700 globally. And like SARS and bird flu, it seems the current strain of coronavirus becomes transmissible before symptoms appear. The latest data comes as the World Health Organization gives the coronavirus an official name, COVID-19. COVID comes from coronavirus, the D stands for the disease, and 19 represents 2019, the year this strain of the virus was first identified. Meanwhile, new research claims COVID-19 may have used the highly endangered pangolin as a vector. Scientists already suspected the virus originated in bats and was then transmitted to humans through another animal. Now, originally it was thought to have been snakes, but the new genetic research indicates pangolins could be the suspected vector. Pangolins are being hunted to extinction for use in traditional Chinese medicines. Of course, these traditional Chinese medicines don't really work, but they have provided a rich source of income for practitioners selling their wu to the gullible. The first patients were infected with the COVID-19 virus through airborne respiratory droplets from animals in the live animal meat markets of the Chinese city of Wuhan, where seafood, poultry, snakes, bats, farm animals, and pangolins are sold. News also that the Wuhan doctor, widely hailed as a hero for trying to warn the world about the deadly potential of the COVID-19 outbreak, has died, allegedly from the infection. 34-year-old Li Wenliang was harassed and arrested by the Chinese government, who accused him of spreading rumours about the virus, when he was in fact sharing accurate information about the disease. Police later forced him to sign a letter admitting that he was spreading untrue speech. There's growing evidence that China has deliberately covered up what it really knows about the contravirus, and when it knew it. Since the first cases back in December, Beijing's been downplaying the severity of the deadly outbreak, censoring reports, removing social media comment on the virus, and telling the public that it couldn't have been transmitted between people, despite them already having clear cases showing that it was, including the infection of 14 hospital workers. More recently, an official press release from the Communist Party's Central Propaganda Department has reported that Chinese leader Xi Jinping has dispatched 300 journalists to Wuhan and Hubei province to educate and provide public opinion guidance to help win the battle to control the epidemic. Turning to other news now, and Antarctica has experienced its hottest ever recorded temperature with a reading of 18.3 degrees Celsius. The new record beats Antarctica's previous record of 17.5 degrees Celsius set back in March 2015. Scientists warned the new record so soon after the previous record is a sign that warming is happening much faster in Antarctica than the global average. It's all a far cry from the olden days, when the lowest temperature ever recorded in Antarctica, in fact anywhere on Earth, was at the Russian Vostok station, where temperatures dropped to a world record minus 89.2 degrees Celsius on the 21st of July 1983. A new study has confirmed that smoking dope doesn't just get you stoned, it can also give you false memories. The findings, reported in the journal PNAS, involved occasional cannabis users inhaling the vapor of a single dose of cannabis or a placebo. They were then asked to perform a series of memory tasks immediately afterwards and again a week later. Scientists found that cannabis appeared to increase false memories for misinformation while subjects were intoxicated. According to the authors, the findings carry implications for the questioning of cannabis-intoxicated witnesses and suspects during investigative interviews. And that's the show for now. SpaceTime is broadcast on Science Zone Radio by the National Science Foundation in Washington, D.C., and through both iHeartRadio and on TuneIn Radio. Or you can subscribe and download SpaceTime as a free twice-weekly podcast through Apple, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Spotify, YouTube, Audio Boom, Podbeam, Android, Castbox, from spacetimewithstuartgary.com, or from your favorite download podcast provider. You can help support the show and the work we do by visiting the SpaceTime online shop and grabbing yourself a few goodies, or by becoming a SpaceTime patron, which gives you access to commercial-free double-episode versions of the show, as well as bonus audio content and other rewards. Just go to our Patreon page through spacetimewithstuartgary.com for all the details. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at SpaceTime with Stuart Gary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.